You're standing on a rock, moving at 30 kilometers per second around a star, which is itself moving at 220 kilometers per second around a galaxy. Everything you've ever known, everyone who's ever lived, every war ever fought, all of it has happened within a bubble, roughly 50 light hours across, which sounds impressive until you find out that the nearest other star is 4.2 light years away. That's not a difference of degree, that's a difference in kind. Let me give you a number that will sit wrong in your stomach. If you took the entire history of human civilization, every year since we scratched the first city into the Fertile Crescent, and you drove that time at highway speed, you wouldn't make it to Alpha Centauri. You wouldn't be close. You'd still have about 4 million years of driving left. And that's the nearest star, the one right next door, our cosmic suburb. People hear this and they nod politely, because we've all been told space is big. But I don't think we actually believe it in our bones. We watch movies where ships zip between star systems, like they're hopping cities, and somewhere in the back of our minds we figure, well, eventually we'll figure out the engine. Eventually the technology catches up. Here's what I want to show you. It's not quite like that. The problem isn't that we haven't built the right rocket yet. The problem is that the universe has rules, and those rules run very, very deep, and some of them are specifically structured in a way that makes leaving our solar system nearly impossible. Not just hard, not just expensive, but genuinely on the edge of what physics permits. Let's get honest about where exactly that edge is. Start with energy. That's where every honest conversation about rocketry has to start. There's a thing called the Tsiolkovsky rocket equation, worked out in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky, who had the misfortune of being completely right. What it says is this: the amount of mass you need to carry as fuel grows exponentially with the velocity you want to achieve, not linearly, exponentially. Here's what that means in practice. Right now, the fastest spacecraft humanity has ever launched is Voyager 1. We sent it in 1977 and used a technique called a gravitational slingshot, swinging past Jupiter and Saturn to steal angular momentum from those planets. Clever. Beautiful even. Voyager is currently moving at about 17 kilometers per second relative to the Sun. To reach Alpha Centauri in a human lifetime, say 40 years, you'd need to travel at roughly 10% of the speed of light. That's 30,000 kilometers per second. Voyager's doing 17. The ratio there is about 1,800 to 1. And because the rocket equation is exponential, to accelerate a spacecraft to that speed using the best chemical propulsion we have, kerosene and liquid oxygen, basically a very elegant, controlled explosion, you'd need a mass of fuel so large relative to your payload that the number becomes meaningless. The ratio of initial fuel mass to final payload mass would be something like 10 to the power of several thousand. There isn't that much matter in the observable universe, so chemical rockets are out, fine. That's not a surprise. We knew that. What about nuclear? We actually designed nuclear rockets. Project Orion in the 1950s proposed pushing a spacecraft by detonating nuclear bombs behind it. This is not science fiction. Real physicists, serious people worked out the engineering. The specific impulse, the efficiency measure for rocket propulsion, would be vastly better than chemical engines. You could potentially achieve velocities of maybe 3 to 10% the speed of light with enough nuclear material. But look at what enough nuclear material means. You need thousands of nuclear bombs. The mass problem doesn't vanish, it just improves. You're still carrying staggering amounts of reaction mass. And there's a deeper issue. At those speeds, the journey to Alpha Centauri still takes 40 to 100 years. You need to keep the ship functioning, keep humans alive, for a span of time longer than most human lives. The engineering challenges are real, but they're not the wall. The wall is what comes next. Let me tell you about the interstellar medium, because this is where people's mental models really fall apart. Space isn't empty. I know you know this, but I mean it specifically. Between the stars, there's a thin gas, mostly hydrogen, a few atoms per cubic centimeter. At low speeds, this is nothing. At 10% the speed of light, it becomes something else entirely. When you're moving at 30,000 kilometers per second through a medium with a few hydrogen atoms per cubic centimeter, those atoms aren't gently brushing against your spacecraft. They are, from the perspective of your ship, a radiation field, high-energy proton impacts, the same physics as a particle accelerator, except instead of sending particles into a target, you're the target and the whole interstellar medium is the accelerator. The shielding required to protect both electronics and any human crew from this bombardment over a 40-year journey adds enormous mass. Add that mass to the calculation and the fuel requirements balloon again. It gets worse. At those velocities, even tiny dust grains, not the thin hydrogen gas, but actual small particles, micron-scale silicates and carbon grains become weapons. A 1 milligram dust particle hitting your ship at 10% the speed of light carries the kinetic energy of a medium-sized bomb. The interstellar medium has roughly one of these particles per cubic kilometer. Over 4.2 light years, traveling through a tube of space maybe 10 meters across, you're going to hit several dozen of them, each impact capable of catastrophic damage. You could put shielding at the front, but shielding is mass. Mass requires more fuel. More fuel requires more mass. The rocket equation spirals. This isn't me being pessimistic. This is the actual structure of the problem. Physics isn't conspiring against us. It's just that the same laws that make chemistry work, the same laws that give stars their energy, the same laws that make radiation harmful to cells, all of them together stack up in a direction that is not favorable to interstellar travel. Now here's where it gets philosophically strange. You might say, fine, forget humans, send robots. Machines don't need air, don't get radiation sickness, don't care if the journey takes 200 years. Send a small, fast probe. No life support, no food, no shielding for biological tissue, just instruments. This is a genuinely better approach. There's a real project, Breakthrough Starshot, that proposes using a ground-based laser array to push a sail-equipped chip to about 20% the speed of light. A gram-scale spacecraft. No rocket equation to fight because you're not carrying fuel. You're being pushed by light from behind. The energy source stays at home. The numbers work out somewhat better. You still need a laser array producing on the order of 100 gigawatts, aimed continuously at a target that will be hundreds of kilometers away within seconds. The engineering is staggering, but not obviously impossible. But here's the problem nobody likes to talk about. You can accelerate, but you can't decelerate. There's no laser array at Alpha Centauri to slow you down. The same sail that catches the laser pushes you to slow down. You'd need to flip around and decelerate, which requires either another laser array at the destination or a way to shed your kinetic energy. At 20% light speed, even a gram-scale probe hitting any kind of material for braking purposes would be explosive. So you'd get there, fly through the system in a matter of hours, take readings, transmit them back, and the transmission radio or laser, traveling at the speed of light, takes 4.2 years to reach us. The whole mission from launch to data receipt over 25 years for the nearest star. A flyby. This isn't nothing. It would be extraordinary, actually, but it illustrates the structure of the problem. Even in the best case, with the cleverest physics we can currently envision, interstellar travel means decades of transit time, flyby observations, and years of signal delay, and that's for 4.2 light years. The galactic disk is 100,000 light years across. Let me get to the real wall now, the one that isn't engineering. Einstein's special relativity is not a theory in the casual sense of a guess. It's one of the most precisely confirmed frameworks in science. Among its consequences is a speed limit, the speed of light in vacuum, approximately 299,792,458 meters per second. Nothing with mass can reach it. This isn't a matter of not having enough fuel. The reason is structural. Here's the operational way to understand it. As you accelerate an object, its relativistic mass increases. The faster you go, the more energy each additional increment of speed requires, and the rate at which it requires more energy grows without bound as you approach light speed. At light speed, you'd need infinite energy, so you can't get there. Now, people hear this and they think about workarounds, wormholes, warp drives, Alcubierre metrics. I want to be careful here because I don't want to replace one kind of mysticism with another. Miguel Alcubierre in 1994 wrote down a solution to Einstein's field equations that describes a bubble of space-time moving faster than light, with flat space inside, a warp drive in the technical sense. This is real mathematics. The equations are internally consistent. It does not violate special relativity because the space inside the bubble isn't moving faster than light. The bubble itself is a distortion in the geometry of space-time. The problem is the energy requirement. To move a bubble the size of a spacecraft at superluminal speeds, the original calculation required a mass of exotic matter, matter with negative energy density, equivalent to the mass of Jupiter, converted entirely to exotic matter. That's the mass of 318 Earths in the form of a substance that may not exist to move one ship, one time. Later refinements reduced this estimate, but reduced still means absurdly large. An exotic matter, matter with genuinely negative energy density, not just matter in exotic states, has never been observed. The Casimir effect produces tiny negative energy densities between conducting plates in a vacuum, but the gap between tiny measurable effect between parallel plates and Jupiter mass of negative energy is not an engineering problem. It may be a fundamental one. The honest position is we don't know if wormholes or warp drives are physically achievable. We have mathematics that seems to permit them. We have no evidence they exist. And the energy requirements, even in the most optimistic theoretical treatments, are in a range that's not usefully distinguishable from impossible by any practical measure. Here's what I find genuinely interesting about all of this. The barriers are layered. There's the chemical energy barrier, rocket equations that demand impossible fuel ratios. There's the mass energy barrier, the interstellar medium that becomes a radiation hazard at the speeds we'd need. There's the relativistic barrier, the speed limit woven into the structure of space-time. And there's the communication barrier. Even if you get there, talking home takes years. Each layer, when you understand it, becomes more interesting rather than less. The rocket equation is beautiful mathematics. The relativistic mass increase connects directly to E-men-c quadrid, which is the same equation that explains why the sun shines. The hazard of the interstellar medium at high speed is the same physics as why particle accelerators can damage equipment. These aren't separate obstacles. They're the same physics looking at you from different angles. And here's something honest I can tell you about this. The reason these barriers exist isn't that the universe is hostile to life. The universe doesn't have intentions. The barriers exist because the same constants of nature that allow chemistry to be interesting, that allow stable atoms, that allow stars to burn at a rate compatible with planetary life, those same constants determine the speed of light, the structure of the rocket equation, the density of the interstellar medium. You can't just dial up one constant without unraveling all the others. The speed of light isn't an arbitrary administrative limit. It's tied to the permittivity and permeability of the vacuum. Fundamental electromagnetic constants. Change the speed of light, and you change the size of atoms, the rate of chemistry, the stability of matter. A universe where you could travel easily between stars at arbitrary speed would not be a universe with stars and planets and chemistry in us. The constants that make us possible are, apparently, the same constants that make the cosmos difficult to traverse. I don't know what to make of that philosophically. I find it interesting. I'm suspicious of people who find it either comforting or despairing because both of those responses are reaching for a significance that the physics doesn't provide. The physics just says, here is the structure of the situation. Here is how hard the problem is. So where does that leave us, actually? The honest answer is that we are, almost certainly, a solar system civilization. Not forever. Timescales of thousands or millions of years are genuinely hard to reason about, and I won't pretend otherwise. But for the foreseeable future, for any reasonable planning horizon, the physics constrains us to the sun's gravitational family. Within the solar system, the situation is entirely different. Mars is 20 light minutes away at most. Jupiter's moons, the asteroid belt, the outer planets, these are places we can reach with known physics in months or years. The rocket equation is hard but not impossible at these distances and speeds. The radiation environment is manageable with known shielding. Communication delays are annoying but workable. The solar system contains 8 planets, hundreds of moons, millions of asteroids, and more comets than we've ever counted. The energy available from a single star is essentially unlimited on any human timescale. There is room here, physical room, energy room, resource room, for a civilization incomprehensibly larger than what we've built so far. The real question isn't, how do we escape the solar system? That's a question being driven by a kind of anxiety, a sense that we need a backup plan, a second address. The real question is, what can we do with what we have? And the answer to that question is not small. But I want to be clear about the other side of this, because intellectual honesty requires it. I've just laid out the physics as we understand it today. We've been surprised before, significantly and structurally surprised, not just technologically but conceptually. Maxwell didn't know about relativity. Newton didn't know about quantum mechanics. There may be physics we don't have yet that changes the picture in ways I can't describe, because if I could describe it, we'd already have it. What I can say is this: the barriers to interstellar travel aren't engineering problems waiting for better materials. They're connected to the deepest structures of physical law we've found so far. If something changes that picture, it won't be a clever engineer figuring out a better rocket nozzle. It will be someone discovering that the universe has structure we haven't found yet. Structure that changes what's possible in the same way that discovering electromagnetism changed what was possible, or discovering the atomic nucleus, or discovering that space and time are flexible. That discovery might happen. I genuinely don't know. Nobody does. But right now, this moment, standing here, we are in a solar system, surrounded by the nearest star for 8 light minutes in every direction, embedded in a galaxy that stretches for 100,000 light years, connected to the rest of the universe only by light that takes billions of years to arrive. The distance to the nearest star isn't a problem waiting to be solved. It's a fact about where we are, and I find that genuinely astonishing, not in a mystical way, not in a way that makes me feel small and insignificant, but in the way that you feel when you finally understand the actual size of something you thought you understood already. The scales are real, the physics is real, and sitting with what's actually true, rather than what we'd prefer to be true, is how you start doing physics that's actually worth anything. The cosmos is not obligated to be conveniently sized for our ambitions.